afternoon or today. Okay. Okay, so we were discussing fracture mechanics, and we have finished the approach, which is based on stress evaluation. There is also another approach, which is based on an energetic approach. Interesting because it allows to us to define a quantity which sometimes can be used in order to make calculation. And this energy-based approach is called Griffith-Crack theory of fracture strength, obviously. So, which are the basic consideration that we have to do in this case? First of all, it's quite an old one because it has been developed just in the 19th. And it is also considered as the, let me say, starting point of fracture mechanics. And it's a theoretical analysis which is based on the consideration that minimum potential energy of classical mechanics and thermodynamics are looking for a total free energy of a system which is in a minimum value in order to have a stable condition. And so it refers to energy and to the principle of minimal energy for stable state. It also assumes, as we have already done at the beginning for linear elastic fracture mechanics based on stress evaluation approach, that the material behavior, also in the Griffith theory, is pure elastic. That is, it can be described with a classical Hooke law. What is going to happen when we think, for example, to a crack propagation? It is going to happen that where the material is broken because of the crack is going to propagate, we have a release of energy, which is a strain energy released. And we have release of energy because we are breaking the materials, which is under an applied load. And at the same time, together with this energy release, elastic strain energy release, if crack propagates, we have the formation of new surfaces. And formation of new surfaces requires energy. So we have two contributions. One is the elastic strain energy released due to crack propagation that is available if it is released. The second one is the energy which is requested to form new surfaces. And thus, considering these two concepts, the theory is based on the consideration that the crack can grow only if the elastic strain energy released due to crack extension is higher than the energy which is requested to create new crack surfaces. This is the basic point for the Griffith theory. Thus, we can translate this concept into some very simple formula, having, for example, in mind the case of a large plate having a central crack and subjected, as in the mode 1 for stress-based linear elastic fracture mechanics subjected to a uniform tensile stress sigma. And we can define some energy quantities. The first is UT, which is the total potential energy in this system. The second one is UI, which is the initial elastic strain energy of the system before introducing a crack, that is, without any crack. The third term, UA, is the change in the elastic energy, strain energy of this system, which is caused by the introduction of a crack. Then we have U gamma, the fourth term of this very simple energy balance, which is the increase in surface energy, which is due to the creation of new crack surfaces when crack obviously propagates. And then we have the final term, which is the work performed by the applied load, that is by the loading system during the introduction of a crack. Thus, we can very easily write that the total potential energy in this system is equal to UI plus UA plus U gamma minus W, that is the work performed by the loading system. We can calculate these quantities which are presented in the very simple equation, because we can remember that if we define, for example, U0 as the strain energy density function, that is the strain energy density per unit volume of our specimen, this is obtained just by considering the area under the stress-strain diagram till the elastic behavior, that is, till the point in which the Hooke law is going to work. Thus, we can write that the total U0 is going to be considered as the integral of the multiplication of the stress sigma per the epsilon, and this leads to the very simple equation U0 equal to sigma with an exponent of 2 divided by 2 times the Young modulus of the materials. And then if we make the integral of U0 in all the volume of the materials, we can define the value of the elastic strain energy of the system without considering the presence of the crack. And so we can write, for example, if we consider that the thickness is 1, that the integral of sigma square divided by 2 times the Young modulus on the volume is just the integral of the sigma square divided 2 times the Young modulus on the area of our specimen, being obviously, as we said, B, the total volume of the body, and B, the thickness of the body. With a very simple approximate, we can also define, then we have also available more sophisticated evaluation methods. We can also define the term UA. If we consider, for example, that's let me say, the first approximation, that being defined the crack, which is this one, okay, having a semi-length equal to C in this case, considering, for example, the hypothesis that the strain energy is released uniformly within a circle having a radius equal to C, that is having a diameter equal to 2 times the semi-crack length, the value of UA on the area using the same formula of before, because this is again strain energy is released, not stored, so the way to write is the same, can be written as sigma square, considered as a constant value, obviously, divided by 2 times the Young modulus per the area of the circle, that is pi Greco per A square. So obtaining this final formulation for the value UA. As I told to you, there are also the possibility to make a little bit more sophisticated, or if you want, complicated calculations by removing this hypothesis of uniformly distributed energy within the circle. This is made by the English approach. Well, just trust me, this is the final formula that we can obtain, that if you can see, it is different from the previous one, which is referred again to an infinitely large plate, having a central crack, now we call it as we have already called, with a total length of 2A, which is equal to the previous one, where we cancel the term 2 on this ratio. For what it concerns the third term, that is the energy related to the creation of new crack surfaces when the cracks propagates, it is possible to define a quantity which is on table for all the material, which is called gamma surface energy density, which multiplied by the surface, the complete surface, gives to us the value of U gamma. So again, in this way, we have one surface, which is 2A of the crack, the second surface with neglecting the crack tip, okay, which is again 2A. The thickness is supposed to be 1. And so if we want to have the value of U gamma, that is the multiplication of gamma with for the surface, we have to just make 2, which multiplies 2 times A, which multiplies 1, that is 4A per gamma. And this is the value of U gamma. For what it concerns, the external work, that is the last term with a minus sign on the general equation. Again, this is a work, so we can make it and calculate it by making this integral, having available the total relative displacement, that we call it, for example, delta, with a force which is just obtained by the multiplication of the applied stress constant on surfaces in which defects are not existing per area of our specimen. And so by having defined the terms of the simple and general equation as previously discussed, we can write the expression of UT like it is reported in this formula, where you see we can have 2 possibilities. The possibilities to work at constant load, that means we are going to have a displacement delta, really, okay? And thus, in this case, the UA term is plus this expression, and the value of W is different from 0. We have to make this integral. Or the case in which we think to have a fixed grip, that is, the specimen is constrained, but in this case, we do have the epsilon, that is the displacement, equal to 0, and thus W is equal to 0, whilst UA is just the expression of before with a minus sign before the ratio. And if we take this as possible consideration for our evaluation, since it is more simple because we can eliminate this term, that is for fixed grip condition. You see here, we apply force, but we do not have a displacement. We can write down the final expression of the UT, the total energy, like it is written here, with W equal to 0 and with minus before the terms UA. And to formulate a criteria for having crack extension, we need to be, as we said at the beginning, at the, let me say, equilibrium point, where the variation of what? The variation of the total energy with an infinitesimal increase of our crack length is equal to 0. And thus we can write a simple derivative equation with which we can obtain this final formula, this one, which is, let me say, the critical point for which we can have a transition from a stable crack to an unstable crack, which is able to propagate. And this final simple formula tells to us that if we are going to consider the first term, which is related to the energy released, the strain energy released, and this second term with gamma, which is related to the energy requested in order to form new crack surfaces, we are at the equilibrium point when the two terms are equal and the cracks can propagate when the first term, that is, the terms which is going to express the energy released, is higher or equal the energy which is requested to create new surfaces, that is, cracks extension. And this can be plotted, obviously, very simply. And so if we put our specimen at the one set of fracture, when we think, for example, that the value of the applied stress sigma is equal to sigma critical, that is the critical far field stress. Remember, far field stress, that is stresses which are calculated here on surfaces where no defects are present, and remembering that we have already used this, we can define two proper Young modulus of the materials depending on the condition which is respected by our specimen. Plane stress, we use a Young modulus equal to the Young modulus, or plane strain, where we use a modified Young modulus by the Poisson ratio of the materials itself. It can be written that the critical stress, far field stress for fracture propagation, is equal to this, in the case we have a plane stress, to the square root of 2 times the Young modulus of the materials multiplied by the surface energy divided by P Greco divided by the semi crack length. Or for plane strain, at the same time, just use the other expression of the Young modulus, again, the square root, where it appears also the Poisson coefficient being used, the Young modulus modified for plane strain. And so in this way, according to this simple approach, which is referred, as you can understand, to mode 1 fracture propagation eventually, with a Griffith theory, we can define the critical stress for fracture propagation. Remember, as we said before, that this approach is limited to materials which have a failure behavior completely brittle and completely elastic, or to be more precise, linear elastic, since we have used the Hughes law, like, for example, most of our ceramic materials, or if you want, polymeric-based materials which are not thermoset, not thermoplastic over the glass transition temperature, which is characterized the simple thermoplastic material. With this approach, it is possible to define also an important term, which is called the strain energy release rate for crack tip, which is called and defined as G. And obviously, we are in this case, in the condition of G1, okay, which is given by this simple general relationship and expresses to us the elastic energy per unit area due to the fact that we have defined the quantities, like said before, per unit area of crack surface, which is made available for an infinitesimal increment of the crack extension. We can define at the same time another term, which is called the crack resistance force, that is R. You see, the first one is related essentially to the strain energy released for an infinitesimal increment of crack extension. This term R is the energy requested for the formation of new surfaces when we are going to think to an infinitesimal increment of crack extension. And so the, let me say, value of R is equal to 2 times gamma. That's what we have written before. R is called also material resistance to crack growth. And usually by the Griffith approach, the instability conditions, that is the possibility to have a crack propagation, is also said very quickly by writing that the strain energy release rate must be higher or at least equal to 2 times the surface energy for the materials itself. And we can define, as we have defined with the stress analysis approach, a critical value of the strain energy release rate, which is called G1C, for example, okay? And this 1C is equal exactly to 2 times gamma. And so we can say that when the strain energy release rate, generally speaking, calculated according to the stresses applied, the crack configuration, and so on, is at least equal to the the critical energy strain energy release rate, which has the meaning of the fracture toughness of the materials. The crack can propagate inside the materials itself. Obviously, there is a relationship between the stress intensity factor K and the strain energy release rate G, defined by the Griffith approach. And again, for example, with this simple case of the infinitesimal large plate containing a centered crack having a total length equal to 2 times A, the value of G is defined in this way. The value of the stress intensity factor, I have not written the geometric factor, but if you want, you can write it inside, is equal to this expression. We have seen it. And so we can derive that the value of the strain energy release rate is just equal to 2 times the stress equal to the stress intensity factor with an exponent of 2 divided by the Young modulus of the materials itself. So they are quantities which are obviously, let me say, not independent, but we can calculate one from the other one. And since some time, we can have available, depending on the textbook, on the manual that are used, the value of G1C, that is of the critical strain energy release rate, which is derived by the Griffith approach with this simple formulation by knowing the Young modulus of the materials, and when it is requested, the Poisson ratio of the materials, we are able also to calculate the the critical value of the stress intensity factor, that is K1C, that we have used up to now. Then that's for elastic. What is going to happen to elastoplastic fracture mechanics, for which we have seen the possibility to have a general, let me say, approach, which is based on the J integral. But the J integral introduces not irrelevant mathematical complications, which can be treated, which can be modeled with advanced modeling tools. But for pre-dimensioning of the materials itself, when plasticity effects at the crack tip cannot be neglected, we can use, let me say, a slightly simplified elastoplastic fracture mechanics, APFM, which is obtained by starting from the linear elastic fracture mechanics with some modifications. And how these modifications are treated in order to have a final formulation which is very similar to those of the linear elastic fracture mechanics, but including also plasticity effects at crack tip. Let me say that this approach can be considered valid when we have, as it is written here, small scale yield. That is, when we can make our hypothesis that yielding is essentially concentrated at the crack tip and not all the specimen as stress value inside, which are approaching or higher the yielding strength of the materials itself. And by using also another constitutive model of the material behavior, which is reported simply here, that is the perfect or perfect elastoplastic model, linear elastoplastic model. That is a relationship within the stresses and the strain in the materials, for which we do have the Hooke law, a linear perfect elastic behavior, till we reach the materials yield strength, yes, or stress, obviously it's the same in this case. And then we do have, let me say, stresses which are blocked with an increase in strain till we have a complete plasticization of all our material. After that, we can introduce the work hardening that we have studied and we have seen, but we are in the case of small scale yield, so plasticity effects which are concentrated at the crack tip, and so we are not considering, let me say, this part of the diagram where work hardening can occur. So this means essentially that when we approach at the crack tip the value of the yield strength of the materials itself, we can consider that this value is blocked, and then stresses are going to increase near the crack tip, where the yield stress of the materials itself is not yet reached. And in this case, one hypothesis which is going to work quite well, which is based on the Irving model for plane stress, like in this case, is to consider the presence of at the crack tip of a circular area in which we are going to reach the yield stress of the materials itself. And we put our coordination system looking to the maximum stress which can be obtained, even though, for example, we want to discuss in polar coordinate. But if you remember the general modeling of the stress field around the crack tip, depending on the theta angle and on the polar coordinate, the f theta function, which is written in the general expression is a function which reaches its maximum value for value of theta equal to 0. That is, we are going to have f theta equal to 1. And so we are going to think that obviously the maximum stresses and the yielding stress is reached where the stresses are higher. And we put at theta ourselves, for our consideration, for these reasons, at theta equal to 0. That is, along the crack line. And by the general expression, we can write that sigma 1 principal direction, which is equal, if we use the xy coordinate system, to sigma x or sigma xx and sigma y or sigma x y, is equal to this general expression. These are the distance from the crack tip, which is equal to Ry or Rx. You can call it as you want. If we are in a condition of a plane stress, this means that sigma zz or sigma z or sigma 3 is equal to 0. And then remembering one of the resistance criteria which we can apply to materials, for example, to ductile materials like the Tresca model, we know that according to the Tresca model, yielding is going to occur when the difference between the two principal directions, 1 and 3, that is the difference between, in this case specifically, y and z, or x and z being y equal to x in terms of stress, is at least equal to the yielding strength of the materials itself. And so we can, by this, say that we can have a first estimation of the radius of this circular area in which we can think that the stress is equal to the yielding stress of the materials and is constant inside. Obviously, we are discussing about, for example, if we are discussing, sorry for the drawing, but I'm just using my hands. If we are discussing about a crack which is made in this way, we need to make this consideration on the right side of the crack, but also on the left side of the crack. This happens in both sides of the crack. But in this way, we can have a first estimation of the plasticity radius of the circular area starting from the crack tip, in which we think that, and we decide, according to this model, that the stress is equal to the yielding stress of the materials itself. We can then make some other consideration. You see here, we are going to block here the value of the stress at the value of the yield stress of the materials itself. And we can make, let me say, also further estimation of the plasticity radius, which is given by a force equilibrium, and which is substantially the same of the first, apart from the terms 2, which is going to be present, as you see here is present, here is not present in the general formulation. So in this case, with the second estimation, which is usually used, the other, let me say, assumption which is made is that the total crack length, if we are in a condition of asymmetry like this one, is given by the value of the pre-existing crack length A, to which we need to sum the value of the plasticity radius. And so we do have an effective, or if you want, modified crack length in order to take into account damages which are due to the presence of plasticity around the crack tip, in the proximity of the crack tip, and finally, by introducing this modified crack length, for which, I repeat, we need to sum to the initial crack length the estimation of the plasticity radius, usually we can use this formula, which is just the same formula of the linear elastic fracture mechanics. You see, we have the geometry factor epsilon, and then we have the stress, which is going to be multiplied by the square root of P Greco multiplied by the crack length, with the only, let me say, modification that the geometry factor must be calculated when we cannot allowed to make the hypothesis of infinite plate for the effective value of the crack length, that is A0 or A at the starting point to which we have to sum the plasticity radius. Sigma, the stress, is again the stress in the far field area, that is on surfaces where cracks are not existing, and under the square root for the definition of this stress intensity factor that sometimes, in order to be, let me say, differentiated by the stress intensity factor, which is calculated by the linear elastic approach, is also called K1P, with a padding P, to remember that we are going to use the effective length of the crack, including the plasticity radius. We have, let me say, a possibility to make all the calculation that we want, as we have done with a linear elastic fracture mechanics, comparing this Kf or K1P with a K1C, that is with a critical value in mode 1 of the stress intensity factor, but including faultily damaged areas due to the plasticity of the materials itself by the estimation of the plasticity radius, which is on the crack tip of the materials itself. So this is a simplified approach, which is going to be working essentially for pre-dimensioning when the small-scale yielding is considered possible, that is local plasticity effect only at the crack tip, not all over our specimen. And again, by knowing the value of the critical value of the stress intensity factor, we can compare K1P or KEF with the critical value of K1 and say that if K1P is higher or at least equal of the critical value, the crack is stable. If it is lower, the crack is stable. This is the most common way in which, let me say, for pre-dimensioning of components, looking to the damage tolerance design approach, they are considered that they are brought inside the theory, the possibility to have plasticity effect at crack tips. Having said that, okay, we can sometimes need to move on an iterative way to solve our problem, even because the value of the geometry factor is depending on the effective length of the crack we have inside the material. But no problem. I mean, the equations are so simple that can be done without any difficulties. This approach is for plane stress, okay? If we are going to make the same approach, and now trust me, for plane strain, Again, according to the Irving models, it is possible to derive another expression of the plasticity radius, which is given by the terms 1 divided, you see here, 18, and then the other terms are essentially the same. Why this is this 18? Because if we are in condition of plane strain, we need to consider the correction given by the presence on the Young modulus of the Poisson ratio. And since most values of our materials, for what it concerns Poisson ratio, they are 1/3, that is 0.3. If we use this, we can have this formula, which is given to us in order to have a force estimation of the plasticity radius. It is also possible to make evaluation in these terms for angular variation of plastic zone radius, that is introducing really the polar coordinates. And in this case, for plane stress, it can be derived this expression. For plane strain, it can be derived this expression. But in all these cases, plane strain or plane stress, the general concept is that we have available simple equation which allow to us to estimate the radius of the plasticity zone. We include this radius of the plasticity zone at the crack tip in the effective crack length that we consider pre-existing inside our materials, and then we move to our verification, to our design, to our calculation, just as in the case of linear elastic fracture mechanics. This is some representation of the difference in plane stress and plane strain plasticity area, depending on the mode 1 of potential crack propagation. So we have also diagrams, but the basic approach is just to have available, very simply, the estimation of the plasticity radius and then make our simple calculations. One thing that must be considered, generally speaking, is that the fracture toughness of the materials usually can depend on the specimen thickness. And the experiments show that by increasing the thickness of the specimen, increasing the thickness, the critical K1 value at fracture decreases. When thickness is larger than a specific value, instead, the value of the critical value, sorry for the repetition, of the stress intensity factor does not change. And this is called, in this case, when it remains constant, so when it acquires the capabilities to be independent from the thickness of the specimen, is called also plane strain fracture toughness, which is the value that we are usually going to use, constant and a material property. And in this case, if we have thick specimens, for example, plane strain, the plastic zone size is smaller, thus less energy is dissipated by plastic deformation, and more energy is available for breaking the atomic bonds, that is, to lack the formation of new surfaces, that is, for crack propagation. And therefore, specimens having larger thickness in plane strain, they exhibit lower fracture resistance. We do have also a relationship in this case. The post relationship, which is reported on this line, is the condition which must be met, where is the thickness of the specimen, in order to make true the hypothesis of plane strain. And this condition can be easily, let me say, verified because it depends, apart from the constant 2.5, by the K1 value and the yielding stress of the materials itself. Generally speaking, we have also a relationship between what we have defined here, that is the plane strain fracture toughness, okay, K1C, which is independent, which is found on the books, and the fracture resistance, KC, in which we do have the dependence on the thickness. And this has been also verified looking to the experimental data. So when this is satisfied, that is when the thickness is higher than this condition, sorry, we are in the hypothesis which can be considered true of plane strain. And when we are in the hypothesis which is considered true of plane strain, we do not have dependence of the fracture toughness from the specimen thickness. If this condition is not satisfied, then we can make the same calculations, but we need to use a different value of the fracture resistance, Kc, which is corrected starting from the constant value K1C, which is corrected according to the thickness of the specimen itself. And the fracture resistance of materials, that is of the component, is thus depending on different parameters, on several parameters. Here I have reported a synoptic representation, qualitative, obviously, for you. If we increase the thickness, the fracture toughness is going to decrease. If we increase the temperature, the fracture toughness is going to increase because the materials is becoming more strain tolerant. If we increase the loading rate, the fracture toughness decreases. And then we have to define, or we can need to define for impact, for example, applied loads, not these values that we are going to discuss, we have discussed up to now, but the dynamic fracture toughness, which is another parameter, since we have a dependence between the loading rate and the fracture toughness value. And obviously, if we increase the yielding strengths of the materials, also the fracture toughness is going to decrease. We remember that by increasing the yielding stress, that is that by making our materials more resistant, it makes or it moves towards a more brittle behavior. And this is also the reason because of for high strength materials, which I used in high performing aerospace applications, most of times the hypothesis of linear elastic or at least elastoplastic approach with the small scale yielding can be used for pre-dimensioning of the component itself, because we are in a situation in which ductility of the materials is not so wide, and ductility effects can be reasonable thought to be concentrated essentially at the crack tip. Oh, sorry. Then fracture toughness. Fracture toughness is a parameter that we found critical value. Obviously, I'm talking about critical value now. Is a parameter which can be found on the books. They are not calculated theoretically, but they are calculated, or if you want, evaluated experimentally. And we have standards which tell to us how we need to make our lab testing in order to calculate or measure and then calculate the value of the fracture toughness of the materials that in which we are interested. We do have American Society and Testing of Materials standard, and here you have the standard to which we must refer for making our lab testing, or for example, British standard. But in any case, we have standards, so we know how we need to fabricate our specimens at lab scales, how we need to test these specimens, how we need to elaborate the experimental results in order to define by the experimental data the fracture toughness of the materials itself. These are some examples that just to give to you an idea of standard test specimens, which are usually used, at least the first two, under tensile loading. we have the so-called CT specimen, which is compact type specimen, in which you see here, we do have very defined geometrical feature of our specimen, a pre-existing crack here, which is usually inserted inside the specimen by a pre-fatigue loading of the specimen itself. Then we have two holes here in which we put inside two cylinders on the upper side and on the bottom side. We apply a tensile force here and a tensile force here, and we are going to monitor the opening here, which is also called crack opening displacement. Opening here, which is obviously in relationship with opening here, okay, where the pre-existing defect is put. We can have a sort of square specimens or a circular specimens, disc here, not disc-shaped compact specimens. But first can be done also by using the SENB specimen, as we have defined at the beginning when we were talking about linear elastic fracture mechanics. In this case, this is a flexural test. It's not a tensile test, but also this is defined by a standard. Or we can have arc-shaped specimens, like in this case, or middle tension MT specimens, which are more similar to our basic, let me say, cases of plate with a center crack pre-existing defects. This is the CT specimen is one of the most used. So as I told to you, we have the specimens, we have specific geometrical configuration, we have a pre-existing crack here, which is caused by a pre-fatigue loading, and then we put all in tensile in order to open the specimen and let the cracks reach the point of propagation. So what we can do, apart from the geometrical configuration here, just for your curiosity, they are a copy of what is written in the standard. You see, all is defined, as in any case we refer to standard for making lab testing. We can record that was the pre-existing crack put by fatigue. We can record the load applied, think for example to a CT specimen, together with the displacement resulting. And depending on the type 1, 2, or 3, we can be able to define a critical value of force for which the cracks starts to propagate, and this value is defined according to what is written here also, and again by the standard, for which we can calculate the value of the stress intensity factor. And when we calculate the stress intensity factor for that critical value of applied load, we are in the condition to define the value of the fracture toughness of the materials itself. We have to use, because most of the time, I would say every time, we are not allowed in these cases to make the hypothesis of an infinite plate. We need to use the geometric factor to be calculated as really, it must be calculated in real condition as a function of the ratio between the half length of the crack and the width of the specimen. But we have for these specimens standardized, for all this, we do have, and it is written in the standard, the formula to be used in order to calculate the geometry factor. Before, okay, no. Okay, they will be later. Okay, let's have a look. Oops. Let's have a look now to these two short video. This is one example of, you see here, crack, which is propagating. You see the crack propagating, in this case, for fatigue. And this is the shape of the specimen. You see here the crack is going to be propagated. This is the extensometer, that is the device which is used to evaluate the displacement and to record the displacement according to, depending on the applied force. And this is another quite example of a propagation. You see here, we do not have any defects, okay? We are inside, in this special case, an aluminum alloy, which is subjected on a CT specimen to fatigue. Have a look here on how fatigue can generate pre-existing crack. Then if we stop, you see here, if we stop to a certain moment, we have generated our crack, and then we make our CT test. Otherwise, if we leave our system work under fatigue condition, these cracks will reach the unstable configuration and then will fracture all the specimen. I was telling to you, this should be before, that the expression of the geometry factor depending on the ratio between the same length of the crack and the width of the specimens are known. This is, for example, the expression which must be used for the band specimen. This is the expression which must be used for the CT specimen. They are written inside the standard. They have been obviously tested and defined also according to measured experimental stress value concentration, for example, with strain gauges, as we have seen in one of our lessons. And thus, by making standard tests, we are able to define which is the plane strain fracture toughness of the materials that we call K1C, that we are able to use without any modification if the condition on the thickness that we have seen before is satisfied. Otherwise, having the real thickness and having the K1C evaluated experimentally, we can define by a simple formula the critical Kc, which is used instead of K1C for our calculations. There are also other conditions which must be met in order to define, let me say, in the standard, in order to use all these equations, set of equations that we have seen in our approaches, which are usually respected, and they are given on the initial length of the crack, on the width of the specimen, on the thickness of the specimens. And this is another, let me say, important consideration, that is the fatigue pre-cracking, which is requested before putting our CT specimen, for example, on the tensile test to evaluate K1C. In order to have reliable results, must be done with a maximum value of the stress intensity factor in the fatigue cycle, which is not going to exceed 60% of K1C. And that's another condition which must be met. So with this, we close the part of fracture mechanics. Now we need to do some little refinement with respect to what we have already started some years ago on the possibility to use fracture mechanic concept in calculation and modeling of fatigue resistance of materials. We have seen some time ago the basic equations. Now I will lead to you other more refined equations. And another things that I want to tell to you is that when we started some years ago to discuss biofatigue, we said, okay, we are thinking to fatigue, and we are limiting our fatigue concept, our fatigue resistance, only, if you remember, to materials which can show ductile behavior. That is essentially at that time for metallic alloys. And we said some years ago, at our stage, some years ago, we could also say that brittle materials, they do not have fatigue resistance. Well, now it's time to remove this simplification because brittle material can have fatigue resistance. Think, for example, just to make one example, we already studied some time ago during these courses when we discussed about the use of silicon dioxide or ceramic-based materials for the fabrication of radome, of flying object to very high speed. Obviously, in that case, we do have fatigue. And so that materials must have, even though the life is very short, but must have a fatigue resistance. That's the case of ceramic materials. And so we just need to see how we can make calculation and which are the differences between ceramic and the standard approach to fatigue for metallic alloys. I have put on this, the following slide, some of the concepts that we have already studied, just to remind to you. So I don't want to spend too much time on this because it has been already started, just to refresh, let me say, your memory about the particular features of a fracture of materials which is broken by fatigue with an initial stable propagation of the crack and then with an unstable propagation, about the definition of fatigue load in terms of amplitude, in terms of average stress, in terms of maximum stress, in terms of minimum stress, in terms of ratio between the minimum and the maximum stress, about the existence, as we discussed, of the potential fatigue limit, which is not existing for all materials, for all metallic alloys, for example. And one class I remember to you of metallic alloys which does not show any fatigue limit are the aluminum-based alloys. Thus, for the aluminum-based alloys, which are in the class of metallic materials, the most important materials for aerospace fabrication of cold, not hot, of cold structure, we need to design taking into consideration a fatigue problem. I remember also that we have defined as a macroscopic approach to fatigue the stress number of cycle diagrams, which are the so-called Bowler curve or Bowler diagram. Here you have some example, for example, for the steel, for the aluminium. You see here aluminium 2024 with a thermal treatment T4 does not have, like in steel here, a fatigue limit, or like in steel here, a fatigue limit, but it has always a defined fatigue life. What is going to say a little bit more with respect to all we have discussed some years ago? That first of all, we need to take into consideration that the average stress of the fatigue cycle, it has an effect. And when the average stress of the fatigue cycle is positive, that is of the sign of a tensile stress, the eventually pre-existing crack will grow faster. And this means that if we are going to take into consideration the Bowler curve, let me say, fatigue life, generally defined as number of cycles for failure and F, is obviously reached earlier if the crack is going to move faster. And thus, there is let me say, there are some models which are going to work quite well, which allow to us to define what is going to happen if we move from the standard fatigue cycle, in which also at lab testing, we take an average stress equal to 0, to a real fatigue testing or fatigue condition where the average stress is not taken equal to 0, but it's positive. In order to define, let me say, for a given, for example, number of failure, if we will work on this, the reduction between the value of the maximum stress applied when the average stress is equal to 0 to the real stress that which can be applied to have the same number of cycles to failure when the average stress is increased to values which are higher than 0. And this reduction, which is referred here, you see, oh, sorry, okay, they have been modeled with Gerber, Goodman, or Soderberg equations. Here you have the times in which they were developed, in which you see here they are reported the values of the average, which is different from 0, and the tensile strength of the material, sigma u, and the initial yield stresses, sigma epsilon at 0, because we are talking effectively, in this case, still of ductile materials, that is, of metallic base alloys. So why this? Because if we have fatigue stress number of cycle diagrams, which are, as in most cases, obtained by lab testing using an alternate symmetric cycle, that is, with an average stress equal to 0, and we want to use that data for designing our component in a condition in which the average stress is not equal to 0, but it is positive, we can use this correction in order to define for a given value of number of cycle of failure the maximum applicable stress, which is called sigma A with asterisk. Okay, so that's, let me say, an improvement with respect to the basic approach of the Wöhler diagram. Another thing that we need to consider is that the stress number of cycle diagram, again, the Wöhler diagrams, cannot be always unique. I mean, we have as a custom to see just one diagram on the stress number of cycle, one curve, sorry, on the stress number of cycle diagram. But since the fatigue rupture, it has probabilistic aspect. When you have just one diagram, usually just one curve, usually that one is referred to 50% of probability of failure. But you can find and you can have available also for the same materials on the same, let me say, Wöhler diagram, different curves to which we can associate different values of probability failure, and then use the curve which fits well our purposes, for example, on the basis of a risk analysis or on the basis of, let me say, indication that we need to respect because, for example, they are standardized. So the Wöhler diagram, they are not only made by one curve, but they can be made for the same materials, for example, by a very high number, we could say also infinite number of curves, depending on the probability failure that we want to associate to the couple stress number of failure of cycles. Another thing that we need to remember a little bit better is the difference between the high and low cycle fatigue. When we have low applied stresses, and then we can expect a longer number of cycles before fracture, that is higher value of fatigue life. And usually this discrimination point is for number of failure cycle around 50,000. We are in the so-called HCF range, that is the high cycle fatigue range. This means that the number of cycles which is requested to break our specimen is a relevant high number. And in these cases, since the stresses are low, we can also expect that the crack tip zone is small, and then that we can apply when we want to make modeling not on a macro scale, but on a micro scale, just looking what is going to happen to the crack propagation. We can apply the concept of linear elastic fracture mechanics or elastoplastic fracture mechanics with the small scale yielding that we have seen today. This cannot be applied. When we do have high stresses, typically stresses which are going also to exceed the yielding strength of the materials itself, for which we have short fatigue life, that is reduced number of cycles between failure. And this is the case instead of the so-called LCF range, that is low cycle fatigue range. So what we usually want to realize is the case of high cycle fatigue, which is the most common. But if for some problems, let me say, we enter in the area of low cycle fatigue, please remember that the modeling are different from those we have already seen, and that now we will refine. In the case of high cycle fatigue, there is a basic relation, which is the so-called Basquin relationship, for which we can say that the amplitude as it is defined for a fatigue load, you see here delta sigma, which is multiplied by the number of cycles to failure to an exponent B, which is called also Basquin exponent, is constant. So we can use for HCF fatigue, for example, a macro, let me say, equation like this one, knowing, if we know the value of the Basquin coefficient and the value of this constant. If we move to the LCF, that is low cycle fatigue, that equation is not more valid. And so we do have another equation, which is called the Coffin-Manson or Manson-Coffin relationship, in which what is going to be constant is not the variation in the applied stress, that is the amplitude on the applied stress, but is the amplitude of the plastic deformation, which is called delta epsilon p, multiplied by the number of cycles to failure with an exponent c. Also, this is constant, and this is the model which can be used if we are going to macroscopical model or want to model macroscopically the LCF fatigue. So you see they are different because here we have the Coffin-Manson and here we have the Basquin relationship, even though please remember that usually we are in our engineering applications in the case of high cycle fatigue, because the life is expected not to be too short. Then we can have some cases in which for a certain period of time the system is going to be stressed according to an HCF, let me say, model. For other period of time, for example, overloads, even short, we can have the necessity to apply on a macro scale the LCF model. And in this case, when we need to take into consideration both for their relative period of time, it is built a total strain life curve, since we do have the Coffin-Manson equationship defined according to deformation, that is according to strain. We convert, you see here, the Basquin relationship by using the Young modulus, that is considering the materials behaving essentially in a linear elastic way in deformation, and we can sum the total deformation in order to have the total strain life curve, in which we report the total strain depending on the number of cycles to failure, which is usually written or designed on diagrams due to the high numbers on a logarithmic scale. Then remember, and then we close today, before next time we will go inside the other models, that the fatigue is affected by many factors. The load spectrum, for example, the stress concentration, for example, the stress gradients, obviously the material properties, the surface quality, the interaction with the environment. What to say more in detail about a couple of these very important factors which can influence the fatigue resistance for the same kind of materials subjected, for example, to the same load. Stress concentration, that's an important thing. Do not overimpose, let me say, do not consider the stress concentration concept equivalent to the stress intensity factor that we have seen discussing about fracture mechanics, because that's another matter. When we have a sort of discontinuity in cross-section of any material, like, for example, in this case, where we do have a curvature radius, if we think to subject this component to a constant applied load, obviously the same applies if the load is cyclically varying, well, due to the presence, that's a question of mechanic of solid, of this cross-section discontinuity here, depending on the radius of curvature, we do have a stress concentration. We are fortunately able to treat analytically, that is, we do have a question to understand how much is this stress concentration, for which we can define a stress concentration factor KT, which is the ratio between the maximum stress and the nominal stress, and is, as I said to you, a function of the notch radius, okay, of the radius of curvature rho. And if the specimen is then subjected to an harmonic, that means to a fatigue load, we have, due to this stress concentration, a reduction on the fatigue limit by the terms 1 divided KT. The experiments in these terms have evidenced that the fatigue life is reduced a little bit more less than this prevision. It is reduced by a factor 1 divided Kf, where Kf is the fatigue strength reduction factor, which is smaller than Kt. So Kt is possible to be calculated. Kf, which is the real reduction in fatigue life, is a little bit smaller than Kt. But we do have, for example, as you see here, example of a simple equation for which we can define the value of Kf depending on the stress concentration Kt which is easily defined by continuous mechanics. Thus, if we have stress concentration, since the specimens which are used on a lab scale in order to define the fatigue limit, they do not have stress concentration. But if we want to use that curves, the diagrams which are obtained by lab testing on real component having a stress concentration factor, we need to calculate the fatigue strength reduction and then use the data with this reduction, which are depending. Here you have two models, one on a material parameter, that is, we need to know these material parameters, or this one, for example, is related to the grain size parameter of the materials itself. Material properties, environment, obviously environment, you can read it, but we can have synergic damages mechanism, for example, by fatigue and by corrosion, or by fatigue and by creep. And then we do have all the topic of the crack growth, which with which we will start on next lecture, essentially for what it concerns, let me say, the possibility to use the micromechanical approach in order to insert in our fatigue modeling the fracture mechanic concept, linear elastic fracture mechanic concept, or elastoplastic fracture mechanic concept, but with a simplified approach, which is related to the small scale yielding of the materials. And by this point, we will start on next Wednesday. Okay.
Professor, I have a question.
Yeah.
About the standard test specimens. So I would like to know which one is the most accurate one.
Well, they are all accurate because you have all analytic solution for the definition of the K1C for all the forms of specimens which are standardized. So there is not much difference. The most common used is the compact eye specimen.
And also I have a question about slide 123. I didn't understand about, you said that when we have a more thicker specimens, there is a, I forget the name that you used. We go to the plastic boundaries is more or less. Am I right?
Can you see it in my screen?
Not now. No.
Okay. Why? Just to understand if, oops, sorry, I will start again if the question is on this slide. One moment. Okay. So you should see now. Yeah.
Yeah.
So which
123 slide, two previous slide.
One moment.
Yes, this one. So actually, I didn't understand the meaning of by increasing the thickness, the critical K1 at fracture will decrease. I would be glad if you can give a brief explanation.
That's first of all, that's an experimental result which show to us that if we increase the thickness of the material, the thickness of the specimen, the critical value of the stress intensity factor, which we call Kc, is going to decrease with respect to the condition to consider that one constant, and in this case we call it K1C, which is referred only to the case of plane strain. Because when we do not have this hypothesis, the stress field distribution depends on the thickness of the materials itself, and increasing the thickness, we can have higher stresses, that is, we can have reduced values of the fracture resistance. And in fact, if you see, we have this. You see this equation?
Yes, Professor.
Oh, sorry. Let me move. Oh. You have this equation, this one, where you start from the constant value, which is related to the plane strain condition, which is a condition met only if this, on the thickness, is respected. And then you have values of Kc, which are going to be decreased if you are going to increase the p-value. That depends on the real stress distribution that we do have around the crack peak, which is different depending on the thickness, because you can move from a plane stress to a mixed mode of opening of the cracks to a plane strain depending on the thickness itself.
Okay, thank you. It's more clear now. Thank you.
Any other question? Okay, if no questions, we will meet again next Wednesday. Good afternoon to everybody.
Arrivederci, prof.
Arrivederci.